All right, finishing up our final video for today is going to be continuing looking at the reactions of esters. So we just looked at hydrolysis of esters in acid solution, and that also involved transesterification if you did it with an alcohol solvent. But if you absolutely wanted to hydrolyze an ester, the best way to do it is under base-mediated conditions. All right, so what we're going to look at is the hydrolysis of an ester in basic media. All right, so we're looking at very high pH, and this is usually achieved by using sodium hydroxide, aqueous sodium hydroxide here. So let's set this up. I'm going to go ahead and take an ester, and I'm going to react this with sodium hydroxide. And this is usually done in water as a solvent. All right. You can add other solvents to help promote solubility, but generally, if you're just talking sodium hydroxide and water, this is totally fine. What you're going to do is you're going to hydrolyze this guy, but since you're hydrolyzing it in base, the instant you form the carboxylic acid, it forms its conjugate base, the carboxylate. All right. So you're not going to get the carboxylic acid yet, and the reason why is because you're in basic media. All right. So if you want to get the acid, all you have to do is neutralize the solution with some acid workup. All right. And workup is something we do in the lab. That's like when you would add acid until it, you see a solid forming, and then you'd put it in an ice bath. All right. So that's what we'd be doing here. And what you would then get is the nice, pretty carboxylic acid. All right, so the hydrolysis of an ester, the way to do that is in basic media. All right, you can do it in acidic, but it works much, much faster in acidic media. Gosh, I just messed up. Much, much faster in basic media, pardon me. All right, so the next set of reactions I want to look at are going to be reactions of the amides. All right. So amides are the least reactive of the CADs that contain carbonyls. All right. So one reaction that we do see, however, doesn't necessarily apply to the other ones. All right. It's the dehydration of an amide. All right, and that can only be done if the amide is primary. All right, the amide must be primary. So what I mean by primary is that you have an amide bond, but the nitrogen contains bonds to only hydrogen outside of the carbonyl. All right, so one reaction that is very helpful there, very useful on primary amides is something called a dehydration. So dehydration is going to be the removal of water. All right, so where in this guy's formula is water? So if we look at the atoms, you got an H there, and an O there. All right, so that's where we're going to lose our H2O. So one of the best dehydrating reagents there are is something we saw in the first semester from the dehydration of alcohols, something called phosphorus oxychloride, or POCl3, and that's going to dehydrate. All right, so what we're going to be left with is an R group, all right, that's bound to carbon, and we've lost oxygen and 2 hydrogens, but we've maintained our bond to nitrogen. All right, and in that process, we're going to form a triple bond to nitrogen. All right, so I'm going to spare you from the mechanism on this one. It's quite involved, but nonetheless, this is dehydration, right? Because what have we effectively lost? Water. All right, so we're going from a primary amide to a nitrile, which again is a carboxylic acid derivative. All right, so a carboxylic acid derivative by definition, again, means what? You can take a molecule, react it with hydrolysis conditions. In the case of hydrolysis of an nitrile, you want H3O plus, all right, and you want this with some heat. What you're going to get is a carboxylic acid, all right. So this is a very convenient way to make carboxylic acids, all right. Is going to be through the hydrolysis of a nitrile group, all right. So this is one reaction that we see nitriles undergoing, all right. So what I want to do now is kind of take a new or do a paradigm shift here where we're going to look at reductions of carboxylic acid derivatives, all right? So reductions of CADs, all right? So that's going to be either achieved with a compound we call sodium borohydride that we saw was able to reduce aldehydes and ketones, all right? Another one we're going to look at is a much stronger version of a reducing agent. This is called lithium aluminum hydride. So if you notice, they contain boron and aluminum. Both are group 13 elements, so these are group 13 hydrides. We call these reducing hydrides, all right? However, the aluminum hydrogen bond is much, much weaker than the boron hydrogen bond, so this guy is much stronger of a reducing agent, all right? Sodium borohydride, if you're careful, you can actually run the reaction with water around, all right? You cannot even think about putting water near lithium aluminum hydride, all right? It will explode, all right? So it is extremely reactive, all right? So when you can get away with using sodium borohydride, do it, all right? But when the conditions require lithium aluminum hydride, be very, very careful, all right? It is explosive when exposed to water, all right? So it takes very special handling conditions and training to use it, but it is effective when you need it, all right? So in essence, we can reduce acid chlorides quite easily with sodium borohydride, all right? So what's going to happen here is we need to think about these hydrides, these group 13 hydrides, as nucleophilic sources of hydrogen, all right? So what are we swapping out here? We're swapping out the chlorine for a hydrogen, all right? That's the essence of these reactions. Oops, I don't know what I'm drawing there. I need sodium borohydride. What we're going to get is replacement nucleophilic addition elimination. So we lose the chlorine and we put hydrogen in its place. All right. So what we get there, this is an acid chloride. Then we get an aldehyde. However, you should recall that an aldehyde is also susceptible to reduction by the sodium borohydride. So we're going to get further reduction to the alcohol. All right. So if you have acid chloride and you treat it with sodium borohydride, that takes that guy all the way down to the the alcohol. All right. So how can we stop at the aldehyde stage? Well, we'll talk a little bit about that here shortly. All right. But this would be not the way I'd want to do it. All right. So if you have an acid chloride and you're going to reduce it, that guy's going all the way down to the alcohol. All right. There's no stopping at the aldehyde by using sodium borohydride. And lithium aluminum hydride is an even stronger reducing agent, and I'd be honest, I don't think I'd ever want to mix an acid chloride with lithium aluminum hydride. That just sounds nasty. All right, so let's just take a look at this mechanism. All right, for reduction, and let's go ahead and look at the acid chloride, and we're going to react it with sodium borohydride. So nucleophilic addition of the hydride to the acid chloride. All right. So now, the main difference here between the reduction of an acid chloride and the reduction of an aldehyde that we'll see shortly is that you have a leaving group here. All right. So this is why we call it addition followed by elimination. Right? You have this leaving group. We're going to kick off the chlorine. All right, chlorine's gone. However, we still have a reactive species here in the aldehyde. The aldehyde can react again with another molecule of borohydride. But now my question is, do we have a leaving group? All right, we look at this guy. If the oxygen collapsed back down, H is our leaving group. No, we don't see that. All right, R can't be our leaving group either. So this is where this guy kind of stops, and that's when we come in with this acid quench to reprotonate our tetrahedral, or sorry, protonate our intermediate that's negatively charged to give us our neutral organic product. All right, so here is our alcohol. So that is how we end up reducing an acid chloride all the way down to an alcohol using sodium borohydride. All right. Another reaction I want to show is going to be the reduction of esters. So esters are a little bit different. All right. They are much, resistant to reduction, all right, relative to an acid chloride, okay? So if you actually take an ester and you react it with sodium borohydride, you get no reaction, right? And the reason why is that the ester is less electrophilic than the certainly less electrophilic than the acid chloride or the ketone. And the reason why is because we have this delocalization of that oxygen, all right, and it's shielding that carbon from electrophilic attack. So we need something that is much more nucleophilic, and that's where lithium aluminum hydride comes in. All right, so as I said before, the bond between aluminum and hydrogen is much weaker, thus much more reactive. And that's what we need to get this guy going. All right, so I'm going to start this mechanism off here by using the lithium aluminum hydride. Now, why lithium in the previous one had sodium? I really think it's a formulation issue. And there may be some lithium aggregates that are involved, but nonetheless, we're not going to be concerned with why lithium and not sodium in this case. But at any rate, we're going to see this reaction that we've seen several times before, all right? And we're going to get oxygen, OR, and our H. Now we're going to simplify this mechanism. There's a much more accepted mechanism that involves coordination to the aluminum and so forth. But for our purposes, it'll be totally appropriate just to go through this type of mechanism here, where we have our tetrahedral intermediate and a leaving group. All right. So we've said before, hey, OR minus, that's a terrible leaving group. All right. Well, that's true. Okay, relative to things like chlorine. Or chloride, pardon me, but now we're dealing with lithium aluminum hydride, which is extremely basic. So a group like OR minus isn't that bad. All right, so we have an aldehyde here, and Sodium borohydride can reduce an aldehyde. Lithium aluminum hydride certainly can. Pardon me, this looks pretty bad. All right. So what do we have so far? I mean, now you have an oxygen that can't kick off anybody, so this thing just kind of floats around until you add an acid. All right. But we need to be careful. What left back here? All right. The OR left. So it's going to still be hanging out over here. Correct? And it's still going to be hanging out over here. And when we come in with our acid quench, we're going to protonate 2 oxygen-containing molecules. There. So how many alcohols do we get out of this? This is an alcohol, and that's an alcohol. So we get 2 alcohols for every 1 ester, right? So 1 ester reduction gave us, with lithium aluminum hydride, gives us 2 alcohols. So how can we rationalize this? Let's go ahead and draw an ester. Let's take ethyl acetate. And let's say we're going to take a 2-step reaction where we take lithium aluminum hydride and we have an acid quench. All right, how can we rationalize the 2 alcohols we're going to get? All right, so what I'm going to do in red is draw a box around the leaving group. All right, and you can imagine that guy leaves, and then under an acid quench, the oxygen gets protonated. So that's our first alcohol. All right, in blue, it doesn't look to me like we're going to have an OH bond forming, but remember, this is a reduction. So in a reduction, one of these the pi bond gets burnt down. All right, so that double bond goes to a single bond. So that's what we're going to get. So the blue hemisphere is going to be what? CH3, C. Now it's not a double bond to oxygen anymore. It's a single bond, all right, to oxygen that gets protonated in the acid step. All right, so what's the rest of the stuff on the carbon? Well, you added hydrogen, all right? So the other stuff you added was hydrogen. Over here in the red, you've got the O, CH2, CH3, and it gets the other hydrogen from the acid, all right? So now what I'm going to do is I'm going to put the green on and say here, all right, those hydrogens come from the reduction, all right, the reduction. Where are those 2 hydrogens at? There and there. They added to the carbonyl carbon. Then in yellow, I'm going to say, all right, hydrogen was added from the acid as well. Where are those hydrogens at? They're from the protonation step. All right, so you need 2 hydrogens from the reduction from lithium aluminum hydride. Then you get 2 additions of hydrogen through protonation from the acid quench. All right, so there's a lot going on here. And you just keep track of where everything's coming from. So going back to the mechanism certainly helps with that, I hope. But remember, reduction of an ester with lithium aluminum hydride is going to give 2 alcohols. All right. Now, reductions of amides. This is a little bit different as well. So we're going to take an amide. I'm going to put 2 R groups on the nitrogen, right, just for simplicity. And if an ester needed lithium aluminum hydride, you better believe an amide is going to need it as well. All right, so how does this guy work? All right, much the same. You get nucleophilic addition. All right. And what do we have now? Well, we don't have a very good leaving group, right? And what I mean by that is, yeah, last time we went in here and kicked off, I'll go ahead and draw it, this, and I'll be able to erase it because this is not what happens. We would lose this guy. This is far too strong of a base, right? So the conjugate acid of this pKa would be somewhere around 35. So this is way too strong of a base. So even though we're in strong base or basic solution, this is not going to happen, all right? So we're not going to actually lose nitrogen in this case, all right? What we actually do is we lose oxygen eventually, all right? So how do we lose oxygen? Well, what ends up happening here is the oxygen coordinates to aluminum, all right, in a subsequent step. So let me get back cleaning up here a little bit, sorry. All right. So we have Al, H, H, and H. All right. So aluminum is sp2 hybridized here, has an empty p orbital, so it's a Lewis acid, so it can accept an electron pair here from oxygen. Oh, that's an H, pardon me. All right. So what nitrogen is going to do now is it's going to kick its lone pair electrons in and shove off this aluminum oxygen complex. So what we wind up with is an imine derivative that we saw last chapter, an iminium ion. And these are susceptible to reduction by lithium aluminum hydride as well. All right. So my question is now, what kind of functional group is this? This happens to be an amide. Oh, sorry, an amine. All right. So this is very interesting. Reductions of amides give amines. All right. Totally different than what we expected. So let's recap that. We take the amide and we reduce with lithium aluminum hydride. All right. What gets kicked out here? That whole oxygen. It's gone. And what's in its place? All right. Single bonds to hydrogen. All right. So this gives us an amine. So reduction of amides with lithium aluminum hydride gives an amine. All right. And finally, the last reduction I want to cover is going to be the reduction of the nitrile. And this reaction would be very similar, but the mechanism is very long, but it's very similar to what we just saw. We can take lithium aluminum hydride and reduce this guy down to an amine as well. All right. So how did this happen? Here, the hydrogens come from the reducing agent. Here, the hydrogens are going to come from the reducing agent as well. All right, so those hydrogens are added via the reducing agent. So are these. All right, so again, to recap, nitrile can be reduced to give the amine, and amide can be reduced to give an amine. So reductions are very important to look at. They're good ways to propose multi-step synthesis that we'll cover later. But for the most part, what I wanted to do with today's videos is introduce carboxylic acid derivatives and a few of their reactions. All right. Thank you for your attention, and I'll be uploading these soon.